today we're going to discuss analysis of frames using slope deflection method. Okay, in analyzing frames using slope deflection method, first we need to identify if the frame will experience sidesway or not. So for this case, the given frame doesn't experience any sidesway because all the joints are restrained. Okay, so whenever if even we have a lateral load applied here, since the joint at E is hinged, so there will be no sidesway. Okay, so this would be an example of a frame without sidesway. So this would be without sidesway. Okay, so we have these frames. So the vertical members has an inertia of I, and the horizontal members has an inertia of 2I. So fixed at A, fixed at D, hinge at E. So there is a horizontal to the right concentrated load at the mid span of this member of 200 kilonewtons, and we have a uniformly distributed load for this member BCE of 50 kilonewton per meter. So we're going to analyze this frame by computing for the moments at all of its joints. Okay, the first step is to assume the direction of the member end moments. Okay, so we initially assume it as counterclockwise to be positive. Let's say for member AB, so okay, so clockwise, this is counterclockwise is positive. Assume counterclockwise positive. So this would be the moment. So here's the moment on AB, while this is the moment on BA. Okay, so likewise for this member DC, counterclockwise. Okay, so this is the moment DC, and while this is the moment on CD. Okay, well, about for the horizontal members, so for BC, so we have it here. Okay, so this is moment BC, while this is moment CB. While for here, moment CE, this one is moment EC. Okay, so these are the member end moments. The next step is to write or calculate for the fixed end moments. Okay, so for member AB, so for the fixed end moments, okay, let's say for member AB, so the FEM of member AB is equal to, we have a concentrated load at the midspan, so that would be PL over 8. Okay, so that would be P is 200, the length is 4 meters divided by 8. Okay, and that is 100. And the fixed end moment for member AB is counterclockwise, so that would be a positive. Then how about for FEM on BA? That would be negative 100. Okay, so that's clockwise. How about for member BC? Member BC is 6 meters length. Likewise, member CE is also 6 meters length. So therefore, they are loaded with the same uniform load of 50 kilonewton per meter. Therefore, its fixed end moment would be just the same. Let's say for BC, that is the same with the fixed end moment on CE. And that would be for uniform load, that's WL square over 12. W is 50, the length is 6 meters, square over 12, and that would give us Okay, counterclockwise is positive, and that is positive 150. Okay, while what about for the FEM on CB? And that is actually the same with the fixed end moment on EC. And they're just the same as negative 150. Okay, what about for member DC or CD? Since we don't have a load on CD or DC, the fixed end moment on CD is just the same with the fixed end moment on DC. Since wala tayong load, the fixed end moment there would just be 0. Okay, so these are the fixed end moments on all of the segments. Okay, next is to write for the slope deflection equation. So we will write for the slope deflection equation, or for the end moment, member end moments for all of these. Okay, let's start with segment AB. Okay, for segment AB, so the moment on AB, okay, so that is, so what is the SDM or the slope deflection equation? So we have 2EI divided by length. The length of this is 4 meters times twice theta A plus theta B minus 3 psi, okay, plus the fixed end moment on AB. Okay, so since point A is a fixed support, therefore this would be 0. Okay, so the rotation there would be 0. And also, points A and B, these joints are unyielding joints, or there is no sidesway at joint B. Therefore, delta there is also 0. So the equation becomes now 2/4 is 1 half. Okay, so that would be 0.5. 1 half is 0.5 of theta B EI, okay, plus the FEM on AB, which is positive 100. Okay, so that would be the simplified equation for MAB. Next, how about for MBA? MBA. Okay, for MBA, so that is, again, 2EI over length, 4 meters. This time, it's B. So, dalawang theta B plus isang theta A minus 3 psi plus the fixed end moment on BA. Okay, again, joint A is a fixed support, therefore theta there is 0. Deflection there is 0 because this is unyielding support, and point B or joint B is doesn't have sidesway. So this becomes 2 times 2 is 4 over 4 is 1. So that becomes EI theta B, then plus the FEM, which is negative 100. So that would be the simplified equation for MBA. Next, how about MBC? MBC. Okay, for MBC, again, that's 2E, but the I or the inertia for member BC is 2I, so I have to multiply it with 2I. Divided by the length of this is 6 meters. Then twice theta B plus theta C minus 3 psi plus the fixed end moment on BC. Okay, so theta B is not 0, theta C is not also 0, but delta is 0 here. So what and FEM on BC is positive 150. So that would be 2 times 2 is 4, 4 times 2 is 8, 8 over 6 is 4/3. So this is 4/3 EI theta B. And for theta C, that is 4 over 6. Or 2/3 EI theta C. Okay, then the FEM for BC is positive 150 plus 150. So that is the simplified equation for MBC. Next, how about for MCB? MCB. That is 2E. Again, the I is 2I for member CB. Divided by the length, 6. This time, we have twice theta C plus theta B minus 3 psi plus the fixed end moment on member CB. Again, deflection or the delta there is 0. Okay, so, and that would be 4 over 6, 8 over 6. Okay, so 8 over 6 is 4 thirds. 4 thirds EI theta C. Then, plus, for theta B, it's 4 over 6. 4 over 6 is 2 thirds EI theta B. Then, plus the FEM for CB is negative 150. Negative 150. So, that is the simplified equation for MCB. Next, how about for CD for this member? Let's say MCD. MCD is here. MCD. Okay, so again, this is 2E. What's the inertia for member CD? It's simply I. And the length is 4 meters times twice theta C plus theta D minus 3 psi plus the fixed end moment, okay, on CD. Okay, since joint D is a fixed support, therefore the rotation there is 0. So theta D is 0. Deflection also is 0 because we have an unyielding supports and we don't have sidesway at C as well. Okay? So, and the FEM for CD is just 0. So what is left is 4 over 4 is 1. So that would be EI theta C. Okay, so that's it. EI theta C. So that is for MCD. How about for DC? Moment on DC. DC. Okay, for DC, that's 2E. Again, the I is simply I lang. Divided by the length of 4 meters. This time is twice theta D plus theta C minus 3 psi plus the fixed end moment on DC. Again, theta D is 0, delta is 0, the fixed end moment there is also 0. So what is left is 2 over 4, or that's 1/2. Okay, 1/2 EI theta C. Okay, so that's 1/2 theta C EI. So that's for MDC. MDC. Now, last segment. How about for CE? So, if you look at member CE or segment CE, this is a rigid point and this is a hinge point. So, we could apply what we use on our previous example, that moment on the rigid point or the rigid point, and this is R stands for the rigid part or rigid point. Yung H naman is for the hinge point. Okay, so that would be 3 EI over L theta R minus psi plus the fixed end moment on RH minus the FEM HR over 2. Okay, so applying this equation or the slope deflection equation for segment CE, so the equation becomes moment on CE, that would be 3 EI, the inertia there is 2I, so that would be 2I divided by the length is 6 meters. Then we have theta C minus psi. Okay, then plus the fixed end moment on CE minus, so dito lang siya naka-pattern, no? Minus the FEM on EC divided by 2. Okay, so let's see. So when simplified, this would become again, delta here is 0. FEM on CE, FEM on CE is positive 150, while for EC naman is it's negative 150. So this becomes 3 times 2 is 6 over 6, so that's 1. So EI, we have EI theta C plus, again, the FEM for CE is positive 150. Then minus FEM on EC is negative 150. Negative 150 over 2. Okay? So this becomes EI theta C 150 plus minus is plus 150 over 2 is 75. So that becomes 225. So plus 225. Okay, so we have here these equations. So let this be as our equation 1, equation 2, equation 3, 4. Okay, this is for 5, this is for 6, and this is for 7. So we have 7 equation. Actually, the last for moment EC. Okay, so what is the moment on EC? Since this is a hinge and this is at the end of the frame, the moment there is just 0. Okay, so actually we have 8 equations. The 8th equation is just the moment there is equal to 0. Now, so what's next? So after writing all the slope deflection equation, the next is to write for the equilibrium equation. Okay, so for the equilibrium equation, or sometimes they are called as the compatibility equations. Okay, so what are the compatibility equations here for this frame? So the summation of moments at a certain joint should be equal to 0. Let's say for joint B, diba? So summation of moment at B is equal to 0. So that means the moment on BA, when added to the moment at BC, the sum of which should be 0. Okay, so we're going to add MBA, that is equation 1, and equation 2. So we're going to add, MBA, this one, equation 2, and equation 3. Okay, so when we add them, these two, okay, so when we add these two, we'll have 1 plus 4 over 3, or 1 or 3 over 3, so that's 7 over 4, 7 over 3, 7 over 3 of EI theta B, okay, then plus 2/3 of EI theta C, then negative 100 plus 150, and that is positive 50 equals 0. Okay, so when we add these two moments, it will yield to this equation. So let me call it as, call this as equation 8, equation 9. Okay, so that's equation 9. So what else? What compatibility equation we can consider? How about at joint C? At joint C, there are 3 members intersecting at joint C. So if we sum moment at joint C, the summation should be also equal to 0. So that means the moment on CB plus the moment on CD plus the moment on CE, the summation of these 3 moments should be equal to 0. So we're going to add these 3 moments. So that is equation 3, equation 4, equation 5, and equation 7. Okay? So, when we add them, so let's say, this is equation, this one, CB, CB, CD, and CE. Okay, so when we add these three equations, in terms of EI delta C, theta C, so that's 4/3 plus 1 plus 1. Okay, so that's 2 plus 4/3, so that's 10/3. So 10/3 EI theta C. Okay, then plus 2/3 of EI theta B. Wala naman theta B rito, wala ring theta B din dito, so that's it. Then the minus 150, walang constant dito. Dito naman is positive 225. So negative 150 plus 225 is 75. Okay, so plus 75 should be equal to 0. So I add these three moments from here. So it gives us this equation. So I'll call it as the equation number 10. Okay? So as you can see, looking at equations 9 and 10, the unknowns are EI theta B and EI theta C. So basically, we have two unknowns lang. Okay, so solving 9 and 10, solving equation 9 and 10 simultaneously. Okay, so it would give us answers for EI theta B as well as EI theta C. So pwedeng gawin mo is yan, since yung constant naman sa theta C, this is theta C and this is theta B. So so if you solve this two, this would give us answers. I'll just give you the final answers. For EI theta B, that is negative 15.91. Okay. Then for EI theta C, that is negative 19.32. Okay. So, yan na yung mga theta B and theta C natin. Then, substituting. So, if we substitute EI theta B and EI theta C in equations 1 to 7. Okay, ito yung equations 1 to 7 natin. They're all functions of EI theta B and EI theta C lang. Alam na natin yung mga values niyan. It could give us the moments at all of these joints. Okay, so giving you the answer, say the moment AB. I'll just give you the final answers. So that's 225 over 22. Okay, so then MBA is negative 1275. 1275 over 11. MBC is 1275 over 11. CB is negative 2050 over 11. MCD 425 over 22. Then MDC is negative 425 over 44. MC is 4525 over 22. And of course, the moment on EC is just 0. Okay? So these are now the moments at all the joints of the frame. So if you want to solve for the joint or for the reactions, you just have to apply statics. Okay, so let's say apply statics. You could solve for the say reaction at X that is 94.03 kilonewtons. That is to the left. The reaction on or the shear on B would be 105.97 kilonewton. This is for your basis lang. And the vertical reaction at A would be 138.26 kilonewton, which is upward. Okay. Then for reaction D, for dx 7.24 kilonewtons, and that is to the right, while dy it's 346.02 kilonewtons. That's upward. Okay, then finally for hinge at E, for the x coordinate, it's 113.21 kilonewton, which is to the left, while its vertical component EY is 115.72 kilonewtons, and that is upward. Okay, so these are the final answers. So hindi ko na pinakita yung detalye ng statics here and the substitution of the values here. So I just want to focus or highlight my discussion on the slope deflection part, method of solution for this frame without Sidesway. Okay, so I hope you learned something out of this example.